Topic we are going to see is about thyristors. So thyristors is a family of devices that are constructed of four semiconductor layers. You have alternative p-type and n-type materials. So the application of thyristor is mainly to use as a switching device. So they are used in control applications like motor speed control, phase control, relay control. We have different types of thyristors. So basic PNPN diode or Shockley diode, silicon control rectifier, diac and triac. These are main types of thyristors. Few are with control and few are without control terminal. The first option shows PNPN diode or Shockley diode. The second option shows silicon control rectifier. Third one diac, fourth one triac, and silicon control switch. This is a structure and symbol for PNPN diode. It is also called as Shockley diode. We have four layers, say P1, N1, P2, N2. Because of these four layers, we have three junctions, junction J1, J2 and J3. This is the diode equivalent for a PNPN diode and a transistor equivalent, two transistors connected back to back with a positive feedback. What happens when you forward bias a PNPN diode? Now anode is given to positive terminal and cathode is given to negative terminal. When you give positive to p-type and negative to n-type, say positive to p1, the first layer, and negative to cathode, so it is obviously junctions J1 and J2. J1 and J3 will be forward biased, and the middle junction, since n-type is given to positive and p-type is given to negative, they are reverse biased. So junctions J1 and J2 will be J1 and J3 will be forward biased and J2 will be reverse biased. Since J2 is reverse biased, the main current that flows will be reverse saturation current. Since only reverse saturation current flows, again we can say that this PNPN diode is in off condition. So the highlighted part in graph shows the off condition now. When you increase the forward bias further, the center junction or J2 junction will go through breakdown because of rise in current, and a particular voltage will be reached, which is called as firing voltage or breakover voltage, which is denoted by VBR. So when you start from 0, you have junctions J1 and J3 forward biased and junction J2 will be reverse biased. When you increase it until VBR, it is a point at a voltage VBR at which your J2 will go into breakdown and switching happens. Switching happens from off state to on state. That is, progressively it is going from off state to on state. And next is how it switches from IS to IH. Once it has a switching, that is, once it goes into breakdown, the switching happens from switching state to holding state, where the device is moving into on state now. So to switch a diode from on to off state back again, we should make sure that IH or holding current is not sustained, which means you should not allow the diode to have IH as a minimum current value flowing in. So again, if I consider the forward bias, when it is increased from 0, the anode current will start to increase slightly until IS, which is again called as off state only. Until IS, it is called off state. The moment it goes into a transition from IS to IH, the switching occurs. So this is cutoff region or forward blocking region. Cutoff region or forward blocking region will cover the portion where we have 0 to VBR and the current is IS, maximum current is IS. This is called as forward blocking region or cutoff state. And the next is negative resistance region. Why it is called as negative resistance region? Because as the voltage increases, the current, normally as the voltage increases, current has to increase. When there is a difference in this proportionality, when there is no when V is proportional to I is not satisfied properly, when it is opposite in such a way that when voltage increases, current decreases, or when voltage decreases, current increases. When either of this condition gets satisfied, this is called as negative resistance portion. So when you see that we have increasing voltage but current is decreasing, so this is called as negative resistance property. So from IS to IH, it goes into this, it goes through negative resistance region. And next is on state. On state is also called as forward conduction region. During reverse bias, the device goes through avalanche breakdown. Two parameters which are important you should know in case of a PNP diode. One is holding current and one is switching current. Holding current is once the 4-layer diode is conducting, that is, it is in the on state, it will continue to conduct or it will continue to remain in that state, on state, only when your holding current is minimized, only when your diode cannot sustain the holding current minimum value. So this is very, very important. Switching current, the value of the anode current at the point where the device switches from off state to on state. The switching current signifies how it goes through a transition from off to on. Before going into holding state or before giving a holding current, this will the device will allow a switching current. The switching current is an indicator where it has to go through a transition from off to on state. And next is silicon controlled rectifier. Silicon controlled rectifier is yet another device which will be using it for uh, control purpose along with the control terminal called gate. So in addition to the structure of PN diode is similar to SCR, the only difference is we have a gate terminal or control terminal here. The symbol is also given. Since we have a control terminal extra, we have given a control terminal in circuit symbol. Here also we have 4-layer P1, N1, P2 and N2. The topmost P layer will act like an anode and the last N layer N2 will act as a cathode. In addition to this, the P layer which is nearer to cathode will act as a gate. When we forward bias an SCR, where we can consider two cases. When gate current is idle, when you don't give any gate current, and when you give a gate current. So when you use this gate terminal, when gate current is 0, it is exactly similar to a normal PNP diode or a Shockley diode. The working of SCR can be just similar to a PNP diode. But when you give gate voltage, when you give gate current, you can either give a positive or a negative one. When you give negative one, since it is a P layer, when you give negative, the reverse bias will tend to increase in J2. So when reverse bias increases, the VBO also will get increased, so that your switching current is is delayed. And when you give a higher or a positive value of gate current, P2 is given to positive or P2 is given to a positive value, so your J2 will be forward biased. That is, the reverse bias is reduced in case of junction J2. So VBO is also reduced. So this gate will control the working of J2. The actual junction J2 reverse bias determines how far you can switch from off to on state and back from on to off state. So this control is very well achieved with the help of gate terminal in case of SCR. Once the SCR has turned on with the help of gate triggering current, your SCR, your gate will not be able to further influence your working. And when we reverse bias in SCR, the anode will be connected to negative terminal and cathode will be connected to positive terminal. So when anode is connected to negative terminal, the topmost P layer will be given to negative. So obviously junction J1 is reverse biased. Similarly, the bottommost N layer will be connected to positive. Again, N given to positive and P given to negative. So J1 and J3 will be reverse biased. And the middle junction J2 will be forward biased. This happens when your gate is open. So most of the current will flow across J1, and when your SCR will, when your SCR crosses this breakover voltage or VBO, J1 or first junction will break down due to avalanche breakdown. That is why even in PNP diode we have seen a graph which shows linear or almost linear increase in current during reverse bias. So one junction will break down or will go through avalanche breakdown to show a large current. So during reverse bias there is no flow of forward current or there is no flow of proper current, significant current through ACR. And what happens when you increase this voltage beyond a critical level? J2 will break down and large current flows which will turn back SCR into on state. This is the graph of SCR which is almost similar to a PNP diode for first option which shows Ig is equal to 0. So which again satisfies the fact that when gate current is 0, your SCR will be exactly similar to the working of a PNP diode or a Shockley diode. The first graph contains again the same cutoff region or forward blocking region, and once it switches from IS to IH, it moves into on state or forward conduction region. During reverse bias, because of breakdown of junction J1, it goes through avalanche breakdown and it shows a high increase in current. When you see second option B for various Ig values, you can see that when your Ig values is greater than, when it keeps on increasing, the VBO is lesser. So when your Ig is 0, the VBO is the maximum. Breakover voltage is maximum for open gate. When you increase the gate current, you attain VBO faster. That is, faster switching happens for higher gate current, which shows that proper biasing or proper triggering through gate current will turn on an SCR faster. These are the performance parameters or performance metrics of an SCR. First one is forward breakover voltage, which is V suffix BR F star. So F denotes forward, BR denotes breakover. The asterisk will denote the condition of the gate or in which condition we are using the gate. So already we know that forward breakover voltage is something that decides or that signifies a transition from on to off to on state. It is beyond this VBO where your SCR or a PNP diode will give a switching current and then move through a transition, go into holding current, which says from SCR is turning on. So this the star will denote 4 options depending upon how you use gate terminal. If it is 0, if your gate is 0, you are giving 0 current to the gate, then it is open circuit. When you are biasing, it is short circuit, yes. When you have a resistor or when it is resistive, along with the triggering bias, when it is resistive, it is called, you have to give it as R. And it is a fixed bias, you have to give V. And holding current is the value of current below which the SCR will switch back to off state, or it will move from conduction state to forward conduction region to forward blocking region or on off state. Forward and reverse blocking regions. Forward and reverse blocking regions are the regions corresponding to open circuit condition for the SCR, which will block the flow of charge from anode to cathode. And a reverse breakdown voltage. So this is nothing but during reverse bias when SCR moves through avalanche breakdown or Zener breakdown, the particular voltage at which breakdown occurs, that is called as reverse breakdown voltage. There are three main methods to turn on an SCR. The first one, as we have discussed, this is nothing but gate triggering or giving a proper biasing to a gate. When you give gate current as 0, it is similar to PNPN. When you give a positive gate current, and when you give a negative gate current, we have seen the conditions and the results, how it shows current in the graph, in the model graph. In addition to gate triggering, we have some more methods, which is nothing but light triggering, DVDT triggering, also called as rate triggering. So light triggering is nothing but using light to trigger or to energize the control terminal gate to switch an SCR from off state to on state. And also you can use temperature, any other form of energy which is nothing but temperature, so that we can influence the VBO, how fast or to make the diode reach VBO, we can either use light or temperature. We also have different methods to turn off an SCR, which is nothing but anode current interruption and forced commutation technique. These are the thyristor ratings. One is latching current. So this is the minimum current required to start the device from off to on state. Say in case of PNPN we had switching and then holding. So like this, here we have latching and then holding. Holding current is something which decides the minimum value which assures that the device is in on state. And finally it is the gate current. It is nothing but the current applied to the gate of the device or control terminal. So it signifies the minimum amount of current, minimum value of current which is used for triggering the device. These are the applications of SCR. So this is basically a switching device. This is not any amplifier. This is not any rectifier. This is only a switching device, and it is mostly applicable only in control applications. So it is used in all type of control, motor control, relay control, wherever you have power transmissions. All those applications you can see thyristors. We have RPS, battery chargers, rectifiers, and static switch. And next is diac and triac. So this is also a two-terminal inverse combination of semiconductor layer, almost like parallel combination of semiconductor layers that permits triggering in either direction. In case of an SCR, it conducts current only in one direction or forward direction. But diac, this is bidirectional. That is, you can see that the graph is similar in forward bias and reverse bias quadrants. In case of SCR or PNP diode, only the forward bias portion, the graph is similar to what we are seeing in this slide. But here we have both the quadrants which indicates forward bias and reverse bias. The graph is similar. That means you can have VBO or breakover voltage both in forward bias and reverse bias conditions. Though the device will be able to conduct in forward bias as well as in reverse bias, it will be able to achieve a significant holding current, switching current, and maximum output current in case of both forward bias and reverse bias. Here you cannot call any of the terminal as positive or negative. We can say that we have an anode 1 or electrode 1, anode 2 or electrode 2. So since we have current possible in both directions, we are having this type of methodology where we don't call a common electrode as cathode and anode. If electrode 1 will act positive, we can say anode 2 will act negative. If electrode 2 acts positive, electrode 1 will act as negatives, and vice versa. Here the breakdown voltages range from 28 volt to 42 volts. The symbol is given, and how you call your terminals anode 1, anode 2 is given, and the structure is also given. And the current levels here is 200 amperes. And the main application for this is proximity detector and touch switch. Next one is triac. This is a symbol, this is the construction or the basic structure of the device. Just when we have seen PNP diode, adding an extra control terminal, we have seen that that is an SCR. Just similar to that, adding an control terminal to diac will give you triac. Here this is also a bidirectional device similar to diac. Extra one difference or one additional property is that it has gate. So here I can have more accurate control, or further control and monitoring can be achieved in case of triac. It is more under my control, or flexible and easy to be monitored. All the and here also you have current passing in both the directions. Current forward bias and reverse bias, you can expect maximum current. This graph shows how change in gate current or change in control current will lead to change in breakover voltage in case of forward bias as well as reverse bias.